right, section 3.3. We're going to pick up where we left off. And we are at the point where we were going to talk about, we already did these, didn't we? There. We're going to talk about the properties of multiplication. So we have talked about properties of addition in whole numbers already. Some of these properties happen again, and we actually have some new properties to add to the list. All right, so the first one is the identity property. We had I'm sorry. On the wrong screen. The first one's a closure property. Yeah, there I am. Sorry, I was in the wrong spot. All right, closure property. We talked about closure before. Closure is the idea that if all the whole numbers were floating around in the air in here, before we did it with addition, we added two whole numbers together, we get another whole number. We don't have to open the door to go get it, right? Because it's still here. Closure works for multiplication the same way. You multiply two whole numbers together, you get another whole number. All right, so for every whole numbers A and B, A times B is a unique whole number. Okay, so tell me what commutative was. Right, so where we can sort of switch the order of the numbers, right? And it's the same thing for multiplication. So for multiplication, if you have whole numbers A and B, then A times B is equal to B times A. You can reverse the order of multiplication, right? 5 times 2 is 2 times 5. Associative property. Gotta have some parentheses. What happens? Say that louder. There's a different grouping inside the parentheses, right? So it's not just that there's parentheses, because sometimes there's parentheses when we have commutative. You guys saw that happen on in section 1. But it's different numbers are inside of the parentheses. So for multiplication, this looks like if you had A times B in parentheses and then times C, this would be the same as having the A on the outside and the B and the C as the group inside. So far, those are all the same properties. We've got one more same property. The identity property. So before with the additive, what was our additive identity? 0. 0 is the number we can add to anything and it does not change. We have a multiplicative identity, and this is the identity value of 1. So there is a unique whole number 1 such that for every whole number A times 1 equals 1 times A, and it equals A. So if I multiply by the number 1, it doesn't change the value. The next three are actually new properties, and the first one is the 0 property. So what happens when you multiply by 0? You get 0, right? So the multiplicative, or the 0 property is that if you have A times 0 or 0 times A, this is 0. And the last two actually are the same thing, they just have a different sign between them. And what they do is they show us a way to combine multiplication and addition, or multiplication and subtraction. And this is the distributive property. The distributive property says that if you have A times B plus C, what does that equal? A times B plus A times C. And we can do it with subtraction just as well. It does really not look any different, right? Except there's a minus sign between them where there previously had been a plus. Okay, seem okay? We're going to do exactly what we did back in section 1. We're going to see some problems where we have to decide what property is being used. All right, first one, what property is that? 0. That's the 0 property. How about the second one? Wow, there's so many rumblings with 3 different answers. Associative. Okay, so there are parentheses, agreed? Okay. First question, do the parentheses use addition or subtraction in them? No. so it's not distributive. Everybody with me on that? Okay, so distributive property has an addition or subtraction inside the parentheses. We don't have that. Second question, associative. Associative property, you just said before, Shannon actually is the one who said it, is that the numbers inside are different if the associative property is used. Are the numbers inside different on this one? No. So this is not the associative property. So what is different? The order of the numbers inside is different. And when you switch the order, that property is the commutative property. Hey, by the way, some of you don't know how to spell commutative. So, I know that sounds silly, but you're actually using words that have other meanings. No, that's because I was talking.
That's why you spell.
Let's try again.
Yes, I got one right.
How's that? Some of you are using letters of N in there, commutative, or communicative, or I'm not sure, but put the T's in there, okay? Commutative property. All right, how about a third one, C? That's associative, right? Different numbers inside those parentheses, but the order's still the same. It goes 7, 3, 4, 7, 3, 4. So this is associative. Part D. That is the identity property. You know what? Let's say it this way too. It's actually the multiplicative identity. It matters now because we've got two identities, okay? How about part E? That is the distributive property.
I have a real quick question.
Uh-huh.
On D, that's not distributed because it doesn't have addition or subtraction, right? Because it could be distributed. Does that make sense?
It only would work because it's the number 1. What
Okay.
you're describing, yes, it is not
Yeah.
the distributive property because there's no addition or subtraction.
Okay.
That's true. How about F? It looks a little funny. It's distributive. Do you see what's happening? The 1 plus 2 is getting distributed to each of the numbers, isn't it? It's a little odd, but that's what's going on. The 1 plus 2 gets multiplied by 3, and the 1 plus 2 gets multiplied by 4. So that is a distributive property as well.
Do we have to put distributive of addition or distributive of subtraction?
Your book may differentiate. I'm okay if you just write me distributive. It doesn't really matter to me. There really is good property. Most books would not differentiate at all.
Okay.
So it's okay if you don't. All right, last topic in this section is division. Okay, multiplication, division, no wrong division. Division of whole numbers. For any whole numbers, A and B, we have to have a couple of conditions. B cannot be 0. I'm sorry, that's the only condition. Then we have A divided by B equals C. If and only if C is a unique whole number such that B times C equals A. These different pieces have different names. A is called the dividend. B is called the divisor. And then C, the answer to a division problem, is called the quotient. And we have some models for division. We've had models for all of them, right? Man, I really wonder if there'll be a test question that has to do with the theory of the model. I'm just thinking out loud, you know. Okay. All right, let's look at a couple of different division models. The first two division models are both called set division models, but they do something a little bit different. And I want to make sure that you see the difference to them because they really are a different way of doing division. All right, so the first one is a partition model. Abby has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? So the kind of picture that you have going on is that you have 24 objects, right? So I'm going to draw you a picture next to the illustration kind of things. We're going to use, we'll use funny shaped rocks today. How about that? Okay. Come on. All right, I have 24 rocks. Do you have 24 rocks? No. Close. 24 rocks. Do I have 24 rocks? I do, don't I? Okay. All right, so the partition model is taking something and partitioning it. That means sort of splitting it into equal numbers of, or into a number of equal groups. So this time I want 6 groups when I'm done. Okay, right? Because I have 6 friends. I want to divide it evenly among my 6 friends, and I need 6 groups of rocks when I'm done. So I need to split them so that there's 6 groups of rocks. I've sort of drawn this in a way that helps me to do that, right? So this is my partition. I've grouped them into 6 different groups. So in this model, in this partition model, what I want is 6 groups when I'm done. How many do each friend get? 4. So the answer to the problem is 4, but this is the concrete picture for what's going on. Okay, I think I need those same rocks. Let's see if I can get them on my next screen. Apparently not. All right. I'm just going to draw my rocks this time. 24 rocks, right? That's too many. I had 24. That was okay, there's 24 rocks. Weren't my previous rocks so much nicer? Oh dear. All right, I have 24 rocks. Stack them together in groups of 6. How is that different than the last problem? Last time I wanted 6 groups. So my goal is to split them into 6 different piles, right? What's my goal here? Just to make groups of 6. What was that word? To put 6 in each group. So if I'm looking at my picture, I want to get 6 into a pile. And here's another 6. And then maybe I have this 6. And then I have this 6 right here. And when I'm all said and done, of course, the answer is still 4. We agreed, right? But the difference was how I chose to split them up. In this way, I actually know how many is in a group. What I want to know, or want to find out, is how many groups I have, or how many, in this case, how many friends get rocks. Now, you've actually experienced both of these kinds of divisions before. These are actually 2 different ways people do groups sometimes. So, when I do groups, usually I decide in advance I want to have 2 people or 3 people or 4 people or however many in each group. And then I sit down with the class roster and I put you physically into groups of that many people. way, right? You guys have all done that in my classroom, so you know that you've done that before. That's this model right here. That is the partition, the model of a variation of the partition model, okay? The other model, and you've done this before too, is where you number off in a classroom, right? Where the teacher goes, count to 5, and you're 1, and we go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and somebody, of course, forgets where they were, and they say 3, no, they're 4, and we have problems because we can count. But we do this kind of thing. And when we do that kind of model, what we know is we know when we're done, we're going to have 5 groups. Because we only gave people numbers 1 through 5, and we say 1's in the back corner, 2's in the front corner, and 3's in the middle, and so forth, right? So by that, we're actually structuring how many groups we have when we're done. We may or may not know how many people we've got in each group when we start that process. Do you see the differences of the two? They're both considered set models, or set partition models, but they do have a little bit of a difference to them. Okay, let me do the next one. The next one is a missing factor model. A missing factor model, we'll read the problem again that I have here. Abby has 24 rocks. She bags them together in groups of 6. If she gives one bag, I'm sorry, I'm reading the wrong one. There we go. Abby has 24 rocks. She wants to give them to 6 of her friends. How many rocks will each friend get? Okay, so same question, but it looks a little bit different. So what does this look like? Well, picture-wise, it looks like this. It looks like the definition of division. We have 24 rocks, and we're going to divide them by something to get 6. It's a missing factor. We kind of did this model with addition and subtraction. Do you remember that? Looks very similar. And so then we fill in the missing factor. And you can do this directly if you knew division facts, but most often when kids are first learning division facts, what they're encouraged to do is to change it into multiplication, which is the definition of division, right? They're asked to say 6 times what, that is, now it's a factor, equals to 24. And if they know their multiplication facts, then they'll remember, oh, I know what that one was. It is 4. So the number that goes in the blank then is a 4. It's the same problem, but it's treating it as a missing factor instead. All right, again, one more example of the same problem. Abby has 24 rocks. Her daughter has a lot of rocks, doesn't she? Yeah. She has more than that, actually. Abby has 24 rocks and she wants to give them to 6 of her friends. How many rocks will each friend get? So what we're going to do here now is we're actually going to draw this out with repeating subtraction. There's a lot of noise on that side today, isn't there? Okay. Crazy people. Not either side. All right, we have 24 rocks. Okay, so we have 24 rocks, and here's the idea. Imagine that you have all of your friends, or all of Abby's friends, lined up in a line. And they're standing in front of her, and they're holding out their hands and saying, I want rocks, I want rocks. Friend number 1 shows up in front of the line. Let's say that her name is Megan. She has a friend named Megan. And Megan gets 6 rocks. So Megan gets her 6 rocks, and she moves away. So we take away 6 rocks from the number of rocks that Abby has. And what would we get? 18. Okay? And then her next friend comes to the front of the line. She has a friend named Ocean. Let's say Ocean comes to the front of the line. Not kidding? For real. Yeah, she's an Ocean. So Ocean comes to the front of the line, and she says, I want my rocks too. And so Ocean gets another 6 rocks. Okay. Great. We have 12 left, you're right. Find another name. She has a friend named Princess. Princess comes to the front of the line. I'm not making this up. You don't make this stuff up.
Where's your
Princess.
Not funny, right?
Yeah, it's funny. Princess is the front of the line now, and Princess wants rocks, so Princess gets 6 rocks, right? And we have left 6 rocks. So she's put that a line of friends because my daughter, she's a popular little girl. And let's see, Adriana. That's not a weird name, sorry. But Adriana's next. Adriana gets another 6 rocks. And if you take a look at this, you can figure out based on the picture how many people got the rocks, right? If we're giving out sets of 6 rocks, and we end up with 4 people.
That one says that.
You're right, I know. But once I started my example, it was already off. So, I know, I'm going to have to fix it now. Let's see if I can fix the question so it'll match the way that I recorded what I just said. She wants to give each friend 6 rocks. How many friends get rocks? Can I change it? We'll get 6 rocks. No problem. The process works the same way, even with the problem set up. This was more fun because you got funny names, right? All right, so here's what we're going to do. We'll do it all together. I won't make you get into groups, okay? So I want you guys to give me some number that we can do like Abby's rocks, and we'll do the different models together. So somebody give me an example.
15.
I'm going to do what? 12 and 3. Okay, so let's use 12 and 3. So let's pick the numbers first. So 12 and 3. What do you want the 12 and the 3 to be? 12 what? 3 what?
12 cupcakes.
Cupcakes, okay. And that's good because 12 cupcakes fit really nicely in a pan, right?
Yeah.
12 cupcakes. Do we want to do 3 friends still?
3 dogs.
3 dogs.
Okay. 3 dogs. All right.
How many cupcakes does it take?
All right. I had a dog once that ate an entire box of the chocolate. See why there's chocolate candy bar thing? An entire box. That was just fine. No problem. All right, set partition model. Okay, so we have 2 different set partition models. We're dividing 12 divided by 3 on all of this stuff, right? 12 divided by 3 is the goal. So how could I describe this, or what would I do if I were trying to describe this or draw a picture of it? Let's do the can't create my word model. All right. What do I want to do with the 12 and the 3? Let's start with that, and then we'll draw the concrete pictures for what's going on. We have 12 cupcakes and what?
3 dogs.
Okay. I have 12 cupcakes and 3 dogs. Okay, now what?
How many cupcakes do each dog?
Okay.
How many dogs will
No dogs are dying today. All right, so how many cupcakes? Whoops.
each dog?
Can each dog eat? And we're assuming that this is an even division. I mean, we're not assuming that one dog gets 5 and one dog gets 9. We're not going to do that, okay? So we're looking at it evenly, okay? There was the other way that we did this when we did 12 divided by 3. Do you remember what it was? How else could I do 12 divided by 3? We're still talking about the dogs, but 3 changes what it means. So I still have, yes, I have 12 cupcakes. What would I do with the 3 cupcakes? Yeah, Autumn's a longer idea. So if I give each dog 3 cupcakes, then what's the question I would be asking myself? How many dogs get cupcakes? How many dogs get cupcakes? All right, and you can picture this, right? So I've got my 12 cupcakes here. And I've got 3 dogs that would be breaking this apart into 3 groups. So it would split here and here. But if I have my 12 cupcakes and I split them in the second way, what am I doing? Groups of 3. Right. Answer's still 4, but you're counting something different, right? Here we're counting the number of groups. Above we were counting the number of cupcakes to get my answer. Okay. Let's finish the last piece in that way. So missing factor. We're using the same word problem. We can use either one of the ones we did above. Do you want to use, let's just pick which one we want to use so everybody's using the same one. Do you want to use the first one with the 3 dogs or the second one with the 3 cupcakes?
3 3 dogs.
The 3 dogs, okay. So if I have 3 dogs, so this is 12 divided by 3, it'll be more particular down here with repeated subtraction. 12 divided by 3, 12 divided by what equals 3. How would I change this to be able to demonstrate it with missing factors?
3 to what?
Right, 3 times what equals to 12, and this value would be 4. Good. And then with repeated subtraction, what would we do? What's the idea behind that? 12 minus either 3 or 4. So we were always doing our division of 12 divided by 3. So let's subtract 3 every time. We subtract what we're dividing by, okay? This will be subtracting 3. This will actually be a model for the second one, even if we wanted to the first, because of the way the division works out. So 12 minus 3 would be
9.
9. Minus 3 would be
6.
6. Minus 3?
3.
Minus 3.
0.
Okay, repeated subtraction stops when you get to 0, and then you count how many times you subtracted. So you subtracted 4 times. So there were 4 dogs that got cupcakes. It would be a model like part B. I live with these, I like part B. All right. A little bit left. Whole number properties of subtraction. Which of the following properties hold for subtraction? Sorry, it says subtraction, it should say division. What happens when you copy paste? Scrap that out, say division. We did it before for subtraction. Everything else is subtraction. Which of the following properties for division hold? Closure property. If you divide 2 whole numbers, do you always get a whole number?
No.
No, give me an example.
12 divided by 5.
All right. No. 12 divided by 5. Do you sometimes?
Yes.
Sure, but not always. And the issue is we gotta have it always happen. Commutative property, does it hold?
No.
No. Give me an example.
12 divided by 3 is 4. 4 divided by 12 is
12 divided by 3 is 4. 3 divided by 12 is actually what? 1/4. In fact, we don't even end the whole numbers anymore when we do that, right? Which was the whole problem on the closure property. How about associative? You had to take a stab in the dark. What do you think?
No.
No. Not going to work. We need to get an example, though. All right. How about 8 divided by 4 divided by 2, and then on the other side would be 8 divided by 4 divided by 2. We'll hope that I didn't pick one out that randomly worked. All right, so what's 4 divided by 2? 2, because we're starting inside the parentheses. What's 8 divided by 2 then? 4. All right, what's 8 divided by 4 in the parentheses? 2. And what's 2 divided by 2? 1. This is no good. Right? Actually, I was still within the whole numbers the entire time on that one. And it still didn't work. Identity property. Yeah?
Yes.
Well,
No.
why no, Beth?
Oh, isn't that the one? Right?
Because if we do 1 divided by 10, that's 1.
Right, so 10 divided by 1 would be okay, right? I'm happy with that. But if you do it the other direction, which has to hold as well, 1 divided by 10 does not equal 10, and so that causes a problem, doesn't it? So that doesn't hold. How about the 0 property? You're just saying no now, but you've got to give me an example.
No, I'm
You know this one?
does not equal 0.
Oh, yeah, that is a big problem, right? So I'm happy with 0 divided by 9. Agreed? Good to go. Kind of like with the 10 divided by 1. But if we do 9 divided by 0, what is that? It's undefined. And if you imagine, here's exactly why it's undefined. This would be like me saying, I have 9 cupcakes and I want to put them into groups of 0. How many groups do I have? How many groups do I have? Groups of 0? I mean, that doesn't make any sense, right? That's kind of part of the problem. All right, how about the distributive property? How about the distributive property? This is the only one that's yes. I knew there
My
was
stats are
one
off.
that's yes.
Figured that many times with no.
All right, this one's a yes, and let me give you an example.
Never mind.
You can't prove things with this example, but I'm going to show you why by example this works, okay? So I'm going to give you some numbers that we can work with pretty well. So let's say that this is actually 20 divided by 10 and then divided by 5. That is not supposed to be divided by, sorry, plus. I'll give you a plus between 20 plus 10. Because again, like we talked about, distributive property has got to have an addition or subtraction and then inside of parentheses. Or we could do this, where we actually do the division to each of the values individually, right? So it's supposed to be 20 divided by 5 plus 10 divided by 5. All right, so what is 20 plus 10?
30.
30. And 30 divided by 5 is 6. What is 20 divided by 5?
Oh.
And 10 divided by 5? And 4 plus 2 is 6. And as long as we pick numbers that will divide by something so that we're still in the whole numbers, right? As long as that's still happening, then this will still hold. I mean, obviously, we could pick something that would end up being not whole numbers, which is not the point. The point is when we are working within the whole numbers, will this work? And the answer is yes. Okay, last one. You ready? Sue claims the following is true by the distributive law where A and B are whole numbers. 3 times the quantity AB equals 3A times 3B. How do you help her? Okay, so what's wrong with what she does have then? Okay, so you guys are saying some of the same things in a little bit different way. So Lauren number 2. Lauren number 2 is saying it doesn't have an addition sign, but you're right. If there's not an addition sign, it's not distributed, right? Or subtraction, okay? And then Lauren number 1 over here, she's saying the 3 should only be there once, correct? Okay, so what's going on?
I'm trying to distribute it, but it's not accurate.
Right, so if you were dealing with this property and if you were dealing with the 3 times AB on the left-hand side like that, what could you do? What properties would hold? And where else could I put the parentheses? Let me say that. Yeah, so you could move the parentheses to be around the 3A, that's associative property, right? You could also move numbers around, the commutative property. But there isn't any distributive property. So all of this sounds really good, but how could you show her that this idea will not work? Okay,
You can't treat them as two separate things.
but they are 2 separate things as well.
Could you just plug in some numbers for
Yes.
example?
Yes. Okay, so one of the first things we'd say is the distributive property. We're going to say what you guys with both Laurens were talking about. The distributive property is for distributing multiplication, and we actually already said it actually works for division too, but multiplication over addition or subtraction, not over multiplication. If we tried this, notice, so somebody give me a number you want to use for A.
2.
A is 2, okay, how about B? 4, sounds good. Then we'd have 3 times 2 times 4, and we'd have to try 3 times 2 times 3 times 4. So what is 2 times 4? 8, and then 8 times 3 is
24.
24. Down here, 3 times 2 is, 3 times 4 is, 12 times 6 is it 72? I think that sounds right. We're going to go with it.
It's 72.
72, thank you. All right, and these aren't the same, right? These just don't match. So, and you might jot yourself down a note, I'll write it here too. This would be a counter example. Showing that three times AB does not equal 3A times 3B. Examples that show something are false is really helpful because you guys can argue all day long about why it works conceptually and be 100% correct and still not really make students believe you. Does that make sense? But if you show them some numbers and show them that the numbers don't work, then they sort of have to believe you. Make sense?
What if you're really bad at improv?
The cool thing is,
make a log for ourselves, like, this definitely does not work.
the cool thing is that most of the time if something doesn't work, it doesn't work for most examples. Most numbers you pick for this are not going to work. If you pick A or B to have the number 1 in them, we might run into some problems. And this one we still might not. But 1s and 0s are typically bad numbers to pick to show counterexamples, and most other numbers usually work. That's kind of just a rule of thumb. Have a great spring break, guys. Group work's on your own, okay? Group work and homework for 3-3 over spring break. Come back with questions on Monday.
I have one